Welcome to the deep dive. Sometimes you stumble across a problem, maybe a really complex equation, and you just think there has to be a simpler way, right? A hidden key.
Exactly. And that's kind of what we're looking at today. We got a listener suggestion pointing towards, well, a potential shortcut for solving a specific, very hefty polynomial equation.
Yeah, so we're diving into this document, aliax2.pdf. It's basically an image showing a theorem.
Right. A theorem by Professor Mourad, Sultan, Ezouidi. And the claim is pretty bold. It supposedly gives the exact roots for a 14th degree polynomial. So our mission is figuring out what this method actually is.
And when you say hefty, you weren't kidding. Listen to this polynomial, px
Right.
equals, okay, deep breath, x to the 14th minus 14x to the 13th plus 91x to the 12th, keeps going, minus 364 by 16 del plus 1001 x kilos minus 2002 by 8 plus 3009 over 21 ek.
And it doesn't stop there. Minus 432 by A minus 6299x NEO plus 6099x0 plus 6099866x plus 2,247,011 equals 0.
Wow.
Yeah. So, I mean, finding the exact roots for something like that, normally you'd be looking at numerical methods, approximations, iterative processes.
Lots of computer time, probably.
Precisely. But this theorem, the one in the image, it claims to offer explicit formulas for the exact roots, just for this one polynomial.
Which is fascinating in itself, is it? Is it common for theorems to be that specific?
For something of degree 14, it's quite unusual, yeah. It makes you think this polynomial must have some special structure, maybe some hidden symmetry that Professor Ezouidi figured out.
Okay, so let's look at these formulas. So suppose keys. The first one is alpha with subscripts 0, 1, and 2, 3, 4, 4, and 5 times x equals, parentheses,
Right.
I sub q sub plus x with a subscript theta of 1, 0, 2, 1, 3, 4, 5, 7, 7, 6, all divided by 14 equals 1 plus fraction. 14 times 1500 to the power of 7 times e all over 7.
Okay, and the second formula is similar, alpha, but with subscripts k times theta of 0, 1, 1, 1, 6 equals, again, parenthesis, I sub q sub plus x subscript k times co divided by 14 equals 1 plus, another fraction, 1 over. 1500 to the power of 7 times e, all divided by 7.
Right. That's a lot of notation. Let's try to unpack it a bit. We see that I sub term in both. Now, the image doesn't explicitly define it, but I0 often implies some kind of initial value, maybe, and Q could be an index.
Could be. And the x terms with those theta functions likely represent parameters linked to specific indices or sets of numbers indicated by theta. Theta itself often represents some function acting on those numbers.
And E is just E, right? The base of the natural logarithm, standard mathematical constant.
Yes. And the alpha values, those are presumably the roots we're looking for. The division by 14 seems clearly linked to the polynomial's degree.
And that constant, 1500 EI, popping up with E, it suggests the roots might involve some, specific exponential values or relationships, perhaps.
It certainly points that way. What's really striking is that these formulas seem designed to just calculate the roots directly. You plug in the parameters, whatever they represent, and out pop the exact solutions.
No iteration, no approximation needed, assuming the theorem is correct. That's the claim, anyway.
Exactly. It bypasses the usual heavy lifting required for high-degree polynomials.
So to sum up this deep dive, we've looked at this theorem presented in aliax2.pdf, attributed to Professor Ezouidi. It offers these two specific formulas that are meant to provide the exact roots for one particular 14th degree polynomial.
And the key thing, the sort of aha moment, is just the idea that a direct, non-iterative method might even exist for such a complex equation. It really challenges the standard assumptions.
It definitely does. Which leads to a final thought for you to consider. If such specific targeted theorems exist, even if they're rare, how might that change the way we approach solving polynomials in fields where exact answers are really important?
Yeah, think about cryptography or maybe certain areas of physics or engineering where approximations aren't quite good enough. Could finding more of these kinds of direct solutions unlock new avenues?
Something to chew on. That's all for this deep dive. Thanks for joining us.